Welcome. The topic of this video is clustering of data using the k-means algorithm. Our objectives are to introduce the k-means algorithm, to illustrate how it works with a simple example, and then point out several considerations that need to be taken into account when using k-means. Clustering is the problem of organizing data into groups. So suppose that I'm given a set of data vectors, a sub I, which are n-dimensional, and I have a total of m of those, then what I want to do is find centroids mu j, and let there be k of those, and k corresponding clusters. This set S sub j are the set of indices I associated with the vectors ai belonging to cluster j. We'll illustrate this idea with a very simple example. Suppose I have some two-dimensional measurements, so n is 2, and I've collected 5 data vectors represented by the points in the plane labeled here 1, 2, 3, 4, and 5. My data matrix A is going to have columns representing these data vectors A sub I, coordinates for each of those. So the first one is at location 1, 2, the second one has coordinates 3, 4, the third one has coordinates 4, 5, fourth one has coordinates 2, 1, and the fifth one has coordinates 5, 3. Given these observed data vectors, we want to organize them into groups. So let's suppose we want to do 2 groups. Group data vectors 2, 3, and 5 together, as I've circled in orange, and assign a centroid mu1. So I've got S1 would have indices 2, 3, 5, mu1 would be 4, 4, and then we'll group these other 2 data vectors together into a set S2 with indices 1 and 4, and a centroid of 1.5, 1.5. Now this is an unsupervised learning problem because we just observed the data. We don't have any labels knowing which clusters each data vector belonged to. Furthermore, the number of clusters in general is an unknown quantity. Now we can think of this in terms of a matrix factorization problem. Represent the data matrix A as the product of a matrix T containing the centroids of the clusters and a matrix W transpose which identifies which centroid is associated with each column of the matrix A. The matrix W transpose will have a 1 in the L, M position if M is an element in the set S sub L representing the Lth cluster. Otherwise it's 0. So in our example that we looked at a moment ago, we had 2 centroids, mu1 and mu2, and we're approximating A as a product of this matrix times another matrix W transpose, which assigns each of these centroids to each column of A. So for example, the first column of A is associated with mu2, so if I put 0 and 1, then when I multiply T into the first column of W transpose, I pick out mu2. So A1 would be approximated by mu2. The second column, A2, is going to be approximated by product of T and 1, 0, which would pick out mu1. Similarly, the third column is also going to be approximated by mu1, the fourth column by mu2, and the fifth column by mu1. The k-means algorithm is an iterative approach to finding clusters. And in this case, we're going to assume that there are k clusters. We'll let these clusters be denoted by Sj, and we put an index I in cluster j if the corresponding data vector A sub I is identified with that cluster. The cardinality, or the number of elements in Sj, we'll write that as the absolute value sign around the set Sj. We'll define the centroid as the average of the data vectors in the cluster. Then we'll define the quality of a cluster based on the coherence, which I'll denote as C sub j, which measures the squared error between each vector and the cluster centroid, summed over all the vectors in that cluster. We can define a global measure of the quality of our clustering using the overall coherence, which is just going to be the sum of the coherences for each cluster. And it turns out that this is the Frobenius norm squared of the difference between the matrix A and this factorization T times W transpose. And the Frobenius norm is a norm that applies to matrices. It's given by the sum of the squares of all the elements in the matrix. So the k-means algorithm follows this set of steps. You start with an initial guess for the cluster centroids, and you can pick those randomly from the available data that you have, and you set the iteration index L equals 0. Then we assign each data vector to a particular cluster if that data vector is closest to the corresponding centroid. Once we have assigned these data vectors to different clusters, we can then update the centroids. And then we repeat steps 2 and 3. Each time we update the centroids, then we go back and reassign the data based on the distance between each data and the new centroids. And we monitor this process. If it converges, then we stop. If it's not converged, we continue iterating. We'll talk about ways to measure whether it's converged later in the video. So let's run a simple example in 2 dimensions to illustrate how the k-means algorithm works. So here I've shown some data in the black circles. I've identified initial guesses for the 2 cluster centroids. The initial guess for the first cluster has this red diamond, and we'll call that mu1, 0, so that's the initialization for that. And then the second cluster will be the blue diamond, and we'll call that mu2, 0. You can see that neither one of these are really centroids associated with the data. Once we have these centroids, we're going to divide the data based on its distance to each centroid. So we'll measure the distance from each data point to each centroid, and we'll assign data to the closest centroid. So in this problem, since we're using Euclidean distance, the perpendicular bisector of the line connecting the 2 centroids will divide the space into 2 groups based on distance. All of the data points below this line we're going to assign to cluster 2, and all the data points above this line are going to be assigned to cluster 1. So we'll make that assignment, and I'll code then these data points with blue circles if they've been assigned to cluster 2 and red circles if they've been assigned to cluster 1. Now, having clustered the data initially, we can then find new centroids associated with these clusters. So I've updated mu1, the center of mass of the red circles, and the second cluster centroid, mu2, has also moved to be the center of the mass of the blue circles. Given these new centroids, we can repartition the data into 2 clusters. We'll assign data to the centroid that is closest to the data vector, and we can visualize this based on the perpendicular bisector. So in this case, data below this solid black line is going to be assigned to cluster 2, whereas data points above the solid black line are going to be assigned to cluster 1 because that's the closest centroid. I've recoded the data representing this new partition into these 2 clusters, S1 and S2, shown in red and blue. Now that I have this new clustering, I can update the centroids. The new centroid be the center of mass, or the mean value of the points in cluster 1 for red, and then the new centroid will be the center of mass of the blue points, which I've denoted by mu2 and I'm showing by the blue diamond. Now that we have the new centroids, we can repartition the data into clusters based on distance from those new centroids. And again, using the perpendicular bisector of the line segment connecting the 2 centroids, we now identify that the points to the left of the black line are associated with cluster 2, and the points to the right are associated with cluster 1. We have the cluster 2 shown in the blue data points and cluster 1 shown in the red data points, and then we recompute the center of mass of each of those clusters to find the new centroid. Now in this case, if we took these new centroids and partitioned the data, none of the data points would be moved to a different cluster, and hence the centroids wouldn't change. At this point, we've converged with this particular example. We are iterating between assigning data to clusters and updating the centroids of those clusters. It's a very simple and efficient algorithm. Now, there's a lot of options and variants of the k-means algorithm. For example, we can use a lot of different strategies to initialize the algorithm. You might decide to randomly partition the data first and then compute a centroid based on the random partitionings. You could pick centroids based on the actual data, or like I did in the last example, I just picked a random centroid. You can use different strategies for termination. You can measure whether the clusters are changing and you stop iterations when the clusters no longer change. You could look at the overall coherence and decide that if the change in the overall coherence from one iteration to the next is below a certain tolerance, that you're going to stop. Or you could simply decide you're going to use a fixed number of iterations. Yet another variation is to use different norms when you assign the clusters. Now, although the k-means algorithm is very simple and is computationally efficient, there's no guarantees that it's going to converge to a global minimum. In fact, it often can converge to a local minimum. So one strategy that people use to minimize the chance of getting a suboptimal solution is to repeat k-means for many different initial guesses of the cluster centroids or clusters, and then picking the clustering based on the initial guess that led to the best overall metric, for example, the best overall coherence. Now, another challenge in using k-means is that in general we don't know the number of clusters in advance. So the strategy here is to try multiple values for the number of clusters and then evaluate the solutions and try to pick one that you think represents the best description of the data. So k-means is a very simple yet can be effective clustering strategy. There are many other more complex clustering strategies also.